everyone. Today we will continue our discussion on phase equilibria, which is on phase diagrams of binary systems. So at the end of this lecture, the students should be able to construct and interpret vapor pressure diagrams for a mixture of two volatile liquids, relate the composition of a liquid and its vapor to the total pressure and to the partial vapor pressures. Use the lever rule to determine from the phase diagram the relative amounts of the phases present. Interpret a temperature composition diagram and use it to determine the course of distillation of a mixture. And lastly, explain the significance of the term azeotrope. For two-component systems, our phase rule becomes F is equal to 4 minus P, or the degree of freedom is equal to 4 minus the number of phases. So therefore, for one phase system, the degree of freedom will be equal to 3. So meaning we will be considering pressure, temperature, and concentration. But the representation of these three variables would require a three-dimensional graph, which is not easy to make. So thus, for convenience, the degree of freedom for this case is reduced to 2 by maintaining one variable, either pressure or temperature, to be constant. So therefore, if either pressure or temperature is constant, our equation would be equal to F is equal to 3 minus P. Now the binary system discussion would be divided into different cases. We have completely miscible liquid systems, and under completely miscible, we have the ideal solutions and the non-ideal solutions. Then second, we will be considering the partially miscible liquid systems, and we will also be discussing the completely immiscible systems. But for this lecture video, we will only be considering the first case. Now, for completely miscible binary liquids, consider a mixture of two components A and B. So we have component A, pure component A, with corresponding vapor pressure, and pure component B with corresponding vapor pressure. If these two would be mixed, how would this affect the total pressure of the mixture? Now, molecules in the liquid phase need to overcome the intermolecular forces of attraction for it to go to the gas phase. So, the escaping tendency would be depending on the intermolecular forces of attraction between like molecules, whether AA or BB, and also unlike molecules A and B. And then also how much of each component there is in the mixture. So therefore, in this solution, or in this type of solution, the molecule A interacts with another molecule A. So this is the same as this reacts with molecule B. So examples of completely miscible binary liquids include ethanol and methanol, benzene and toluene. So example, if we have more A in the mixture, the total pressure of the solution will have a greater contribution from molecule A. Okay, for liquid vapor equilibrium in ideal solutions at constant temperature. So in an ideal solution, the components in the liquid phase are in equilibrium with the components in the vapor phase. So if this is in equilibrium, we know that the chemical potential of each component is the same in each and every phase in the system. So the chemical potential in the liquid is equal to the chemical potential in the gas phase. So therefore, if we will be considering the total pressure of the vapor phase in contact with the solution is dependent on the concentration of the components in the liquid or solution phase. So therefore, if we have two components, the total pressure of the solution is equal to partial pressure of component A plus partial pressure of the component B. Now, recalling Raoult's law here, so in Raoult's law, the partial pressure of a component in the vapor phase is directly proportional to its mole fraction in the solution. So in terms of equation, partial pressure is equal to the product of vapor pressure of that component multiplied by its mole fraction. So you know that the total pressure is equal to A partial pressure of A plus partial pressure of B if we have two systems. So replacing in this equation, the expressions for the partial vapor pressure of each component as stated in Raoult's law yields total pressure of solution is equal to vapor pressure of A multiplied by mole fraction of A plus mole fraction of B multiplied by its vapor pressure. So since we only have two components here, if we will be replacing x of b in terms of x of a, so 1 minus x of a, our equation becomes P of solution is equal to PB asterisk plus the difference of PA minus PB, vapor pressures of A and B multiplied by mole fraction. Okay, so examination of the final equation reveals that it follows the form of the equation of a straight line. So Y here is your pressure and X is your mole fraction, and your slope is a difference of the vapor pressures of A and B, and your y-intercept is equal to vapor pressure of B. So if there are two functions that are being plotted in terms of pressure and mole fraction, a straight line results as shown in this figure. Now, for liquid vapor equilibrium in ideal solutions at constant temperature, so considering the composition of the vapor phase, so recall Dalton's law here, Y of A is equal to P of A over P of solution. So the composition of the vapor component A is equal to partial pressure of A over total pressure of the solution. So replacing the equation, P of A in terms of Raoult's law, so we would be getting this term. So you know that, recall Raoult's law earlier, and then combining the Raoult's law and Dalton's law, we would be getting, we would be expressing x of A. So substituting this expression for P and solving for XA gives this value. And putting this in expression for x of A in the box equation. So solving for P, this yields an equation that relates P and Y of A. So it is obvious that the total pressure is not a linear function of the vapor composition. So when P is plotted against Y of A, a curve bent upward would be obtained as shown in the figure. Now let us try to solve sample problems. At 60 degrees Celsius, the vapor pressure of ethanol is 352.7 millimeter mercury, and that of methanol is 625 millimeter mercury. Ethanol and methanol form an ideal solution. So for a liquid solution that contains 60% mole ethanol, calculate the vapor pressure of the mixture and the composition of the vapor in equilibrium with the mixture. Letter C, the composition of the last drop of liquid before vaporization becomes complete, and the pressure at which mixture will completely vaporize at 60 degrees Celsius. So for our solution, to get the vapor pressure of the mixture, so P of solution is equal to the partial pressure of ethanol plus partial pressure of methanol. So using Raoult's law, mole fraction of ethanol times vapor pressure plus mole fraction of methanol multiplied by its vapor pressure. So we will be getting 461.6 millimeter mercury. For letter B, what's the composition of the vapor in equilibrium with the mixture? We already know the vapor pressure of this, the solution. So this is partial pressure of ethanol divided by total pressure. So we will be getting 0.458. Now for the last, the composition of the last drop of liquid before vaporization becomes complete. So we would be considering the Y prime of the vapor component of ethanol is equal to its original composition, which is equal to 0.6. So substituting the equation, the partial pressure of the vapor of ethanol over P of the solution. So we would be solving for the X prime here. So what is the component of the liquid ethanol if Y prime is equal to 0.6? So substituting in the known values from the equation, we would be getting 0.727. And what is the pressure at which mixture will completely vaporize at this temperature? So substituting, we would be getting 427 millimeter mercury. Now, the dew point line, so this is the curve occurring at low pressures. So in terms of, so this is called the vapor composition curve. So the curve occurring at low pressure, so this is the dew point line here as represented by this figure, and the area below it includes points corresponding to the system which contains, at low pressure, we have vapor phase. So the curve occurring at high pressures, so we call it the liquid composition curve or the bubble point line. So this is the bubble point curve here. So the area above it contains points corresponding to a binary system which contains a liquid phase. And then the area enclosed by two curves includes systems wherein a liquid phase coexists and is in equilibrium with a vapor phase. So if you are considering the first trace of vapor, you will be referring to the bubble point line. So this is an example of the graph for pressure versus mole fraction at constant temperature. So note that the composition of the two phases is dependent on the pressure and is independent of the overall composition of the mixture. So observe also here in this figure that the vapor is richer in the more volatile component A than in the solution. So as long as the pressure is kept constant, the composition of the phases remains the same, even if the overall composition is varied. So take note of that. So as long as we keep the pressure constant, we would be getting a unique tie line. So note that the two phases that are in equilibrium with each other, so are joined by this line. So, and this line is also known as tie line, which is unique for each pressure. Now, let us continue our discussion on the Lever rule. So the Lever rule is used to deduce the relative abundances of each phase in equilibrium. So while the composition of the two phases in equilibrium remains the same, as the overall composition is altered to a fixed pressure, the relative amount of liquid in the vapor phase changes. So example, if the total number of moles in the components, so let us assign this as moles in the liquid phase, and this is the moles in the vapor phase. So the sum of this is equal to the total number of moles of the component. So we can expect that by law of conservation of mass, so if we will convert this to mass, so we will have something like this. And then carrying out a mass balance on the component, A dictates that amount of A in the mixture is equal to the sum of A in the liquid phase and A in the vapor phase. So example, if we have a composition represented by D and then pressure at P1, so X in terms of P1, so we have point D. So extending the line here, so this is the composition, composition in the vapor phase, and this is extending this to liquid line. So we have X sub 1 here. So the ratio of the moles of liquid over moles of vapor phase is equivalent to line DA over the measurement of line CD. So this Lever rule is very important because this shows the ratio of the amount of liquid phase to that of vapor phase that is being determined by the overall composition of the mixture. So this principle is very important, not only for completely miscible liquids, but also in the latter part of our discussion. Now, what about liquid vapor equilibrium at constant pressure? So take note that this condition is commonly encountered during distillation. Commonly, this pressure is set at 1 atmosphere or 1.013 bar, and the temperature under this condition is what we call the normal boiling point of the liquid or the boiling point diagram. And the normal boiling point of a solution, if you don't know it yet, the value can be calculated through the Clapeyron equation. So after having discussed LV equilibrium or liquid vapor equilibrium at constant temperature, so let us now consider this equilibrium at constant pressure with composition and temperature. So the graph is T, temperature versus mole fraction. So it should be realized that the pressure here refers to the vapor pressure in equilibrium with the liquid phase, and therefore is actually the vapor pressure of the liquid. Now, by principle, a liquid with low vapor pressure at room temperature, so what is the effect in the temperature? So this is it has a high boiling point. And if the liquid has high vapor pressure, it will exhibit a lower boiling point. So since the total vapor pressure of the solutions is dependent on the composition of the solution, it follows that the boiling point of the solutions will vary with the composition of the mixture. And solutions of different concentrations, take note, this will boil at different temperatures. Now, if we will try to compare the pressure composition phase diagram with the boiling point diagram, so number one, in the boiling point diagram, none of the curves is straight line, as you can see in the figure. Now, the liquid region is found at the bottom here of the boiling point diagram. So this makes sense because at constant P, the liquid state is more stable at low temperature. So whereas in the pressure diagram, the liquid area is at the top. Next is the liquid composition curve, or the bubble point line is the lower curve here. And the vapor composition is the upper curve in the boiling point diagram. Okay? And then the positions are being reversed since we have opposite phases here in the pressure composition diagram. So the labeling of curves and the areas in these two diagrams, take note, this could be made simpler and less confusing by remembering that liquid state is favored at low temperature, which makes sense, and at high pressure. And therefore, the vapor phase or state is preferred at high temperature and low pressure. Now, let us try to solve sample problem number 2. At 100 degrees Celsius, the vapor pressure of pure benzene is 180 kPa, and that of pure toluene is 74.2 kPa. Calculate the mole fraction of benzene in a benzene-toluene mixture that will have a normal boiling point of 100 degrees Celsius. And then the mixtures of benzene and toluene, so they exhibit ideal solution behavior. So P total is equal to partial pressure of benzene plus partial pressure of toluene. So substituting using Rolle's law. And then we know that the P total here is equivalent to 101.3 kPa. So this is, take note of this. And then mole fraction multiplied by corresponding vapor pressures of benzene and toluene. So we will be getting X sub B equivalent to 0.256. Okay. Now for liquid, so to continue, so we still in the constant pressure condition. So note that, so let's recall the boiling point diagram. So this is how it looks like. So if the mixture is, let's say, kept at T sub K, so this is at this point. So you will notice that entirely the system consists of liquid. Now, when the mixture is heated, so let's say we will increase it to L, represented by point L, and then the temperature is T sub L. What happens in our mixture? It starts to form a vapor. A trace of vapor will finally appear that has the composition. So extending here, the tie line at Y sub L. So if the temperature is further increased to temperature T sub M, okay? So represented at this point, okay? The mixture will split into liquid and vapor. So in terms of point M, extending the tie line, we have X sub M here and Y sub M in the vapor phase. So upon heating the mixture, let's say at point N, heating the mixture some more until it reaches T sub N, the last drop of the liquid phase will now vaporize. So the question is, the last drop of the liquid will finally vaporize. So you will consider this point N. And if the temperature is further raised to 0.0, so what happens? The system or our mixture will consist only of vapor phase. Okay, so this is how you analyze the boiling point diagram. So for the application, the boiling point diagram can also be used to describe the changes that take place when the ideal mixture is subjected to distillation. So during distillation, the liquid mixture is heated continuously and the resulting vapor is removed, and then the resulting vapor is removed from the system by directing it to the condenser where it is converted into liquid. So under this condition, we could say that the system is an open system. So since the vapor escapes into the condenser and the overall composition of the system in the distillation still is changing. So if the solution is heated initially, it will start to boil at T sub 1, okay? And then at this temperature, a vapor composition of Y here is being formed. So note that the vapor is richer in the more volatile component A than in the liquid. Then the vapor escapes in the condenser. The system remains in the still, or we also call it residue. So it becomes poorer in component A. Okay? So this liquid will require a higher temperature for it to boil and form a vapor which goes to the condenser. So this process will take place continuously until the final residue will consist of pure B and will boil at T sub B, which is the boiling point of pure B. Okay? So during distillation, the vapor goes into the condenser where it becomes a liquid. So, okay, and the above succession of vaporization and condensation that takes place during the process is what we call fractional distillation. So fractional distillation results in the separation of more volatile component. So we call it as the distillate from the less volatile component B, which is obtained in the final residue. Okay? So in this two figures, so you will see that in order to achieve a maximum separation, so we need to determine the number of theoretical plates or the steps needed to bring about a specified degree of separation of two components in the mixture. So in this figure in the left, we have number of theoretical plates equal to 3. And in the figure on the right, so we have equal to 5. Okay. Now, what about for non-ideal solutions? So not all liquids behave like ideal mixtures and exhibit liquid vapor equilibrium properties similar to what we discussed in the previous topic. So a common example is ethanol water system. So the solutions which exhibit a maximum or minimum boiling point are what we call azeotrope. So for this system, their boiling point diagrams feature a maximum or minimum boiling point at a certain concentration. So this is what we call the azeotrope. So we have what we call the maximum boiling mixtures. So examples of this include benzene and ethanol, trichloromethane ethanol, water propanol, and benzene cyclohexane. Then examples of minimum boiling mixtures include trichloromethane acetone, pyridine acetic acid, water hydrochloric acid, and water nitric acid. So what is the difference in terms of figure from the one we discussed above? These mixtures have another peculiar behavior. So in the sense that their boiling point, so at this point, the vapor form has the same composition as the liquid phase. So as a result, it's not possible to separate the two pure components in these mixtures. So in ideal solution, recall that the vapor composition curve is found in the liquid composition diagram. For non-ideal, the curves here intersect at one point, so indicating that the liquid solution is identical with the vapor composition. So this is what we call the boiling point of the azeotrope. So liquid region is in the lower part of the diagram, okay? and the vapor region is in the upper part, of course, representing its behavior in terms of temperature. So liquid is more stable at lower temperature and vapor is more stable at higher temperature. So similar with ideal solutions, the region between the two curves corresponds to the system contain a liquid in the vapor phase. So at this point. So in the high boiling azeotrope, this is at this point, and the low boiling azeotrope at this point. Okay, so for systems exhibiting a maximum boiling point diagram, so we will this will yield the distillate as the pure A and B, and your residue is the azeotrope. And then for systems exhibiting minimum boiling point diagram, so it's the other way around. So the residue is the pure A and B, and your distillate is the azeotrope. Okay. Now for ideal mixtures, the vapor phase is richer in the more volatile component than in the liquid phase, but this is not happening in non-ideal solutions. For system exhibiting a maximum boiling point mixture, okay, in this case, so below the concentration of the azeotrope, so the vapor is richer in the less volatile component. However, for systems exhibiting a minimum boiling mixture above the concentration of the azeotrope, above, no, the vapor is richer in the less volatile component. Okay, so for system exhibiting a maximum boiling point, okay, the more volatile component could be any of the pure components, depending on the overall composition of the mixture. And for systems that has minimum boiling point, the more volatile component is the azeotrope. So what is the significance now of the azeotrope? So this represents a maximum in which we could have an effective separation of the mixture. Take note in the ethanol water case. So example, in the ethanol water system, it forms a minimum boiling point mixture containing 95% ethanol. So the formation of the azeotrope is the reason why it's not possible to obtain a pure ethanol or absolute ethanol in the distillate during fractional distillation of aqueous solutions of ethanol with concentrations lower than 95. This could only be obtained after increasing the ethanol concentration to above 95 by treating it with a metal. So common example here is a sodium metal. So in the ethanol water system, it is forming an azeotrope at 95.6% ethanol, and the corresponding temperature is 78.2 degrees. So in the case of nitric acid water system, it's forming an azeotrope, okay, at 68% nitric acid and 32% water, and the boiling point is 120.5 degrees Celsius. So overall, so these are the discussion for miscible binary liquids, both ideal and non-ideal. So in the continuation of our lecture, we will be considering partially miscible liquids and immiscible liquids.